Hello everybody, my name is Malkiet and I'll be giving this presentation on Zephyr device driver structure, which is basically the device driver structure in Zephyr operating system with respect to its implementation on Galileo boards, because we've already worked on the Galileo board. So let's move ahead with this. So we have a device driver in Zephyr. All the device driver, we have different device driver in Zephyr, which are all statically defined, and all the device drivers are stored in Zephyr based drivers. We could see different device driver there. There are UART, SPI, I2C, and there are many more device driver, and they have specified as they have given us these certain generic like API, so that we are able to use that device drivers. So, uh, s- so we like let's talk about the driver initialization. Now, whenever a driver is initialized, it basically fills the device start pointer containing the function pointer to its API. So what it does is, like, suppose whenever a driver initializes, what it'll do is, like, it'll give us a device. It'll just give us a device pointer, which will be like this structure mentioned here. Like, this is the device structure, and it'll have a config, some APIs containing the functions, and then some driver data. So what it'll do, it'll like create this device and just return us the API, like just return us the pointer to this device so that we can use it. So whenever we try to initialize a driver, we just have to mention the name of the driver. It'll give us the device pointer, which we can later use, and we can add configuration to it, and it'll have a specific API already attached to it, and we could fill some driver data inside it. And what it'll do, considering that everything is statically defined at the initialization, so whenever the kernel is booted, the driver gets initialized and we get this pointer. So that's how it goes. So all the drivers are statically initialized, so just at the time of booting we can get a pointer and we could use it in our code, in application. Yes. And device driver in Zephyr. So we have different device driver present, which are present on all supported board configurations. There's some device driver on all board configurations, which is basically an interrupt controller, which will control the kernel's interrupt management, all the interrupt service routines. And, like, we have different controllers, and it is also providing different controllers, interrupt controllers, depending upon the usage. We also have timers. So this device driver uses the kernel system clock, hardware clocks, and we could have different timers, or we have to get clock ticks and everything. API for all this stuff is given in this timer device driver. And for serial communication, we also have a device driver for serial communication. Like, in we have to access the console subsystem. Like, we have this assignment for part 1. We try to build a console on it, and in that console we actually have to give in commands and use the operating system basically. And we are able to have a serial connection to that Galileo board only because of this serial communication. So this driver basically provides us with serial communication, so that we are able to communicate with the console with what we have written. Like, we had console taking in commands like dump and enable. So we are able to use all those commands using the serial communication. We had this random number generator. Now, this is just a device driver that just provides with a source of random numbers. And device API, like mentioned before, we have device initialization, which give us which um, which are statically initialized at the boot time. So these are the APIs to initialize the driver. So if we make our own driver, so we have to use these device initialization for them. So this is device init, like almost all of the devices are used, almost all of the drivers that are already used in Zephyr kernel, like all the stock drivers that we have, use this API device underscore init. And then we have another API device underscore and underscore API underscore init, which basically creates a device object and set it up for boot time initialization, but it takes a pointer to driver API. Like we have a structure that contains all the functions. We have the structure which contains the function pointers, and this API, basically this device and API init also takes this as input so that it knows where the driver API is. So device name get, it is to get the name of a device driver, and device underscore get, it's to obtain the pointer to a device by name. So we just give a name and it will just return the device pointer. And then device declare is to declare a device object. So let's talk about the I2C interface. Now I2C interface is responsible for communication the I2C bus and Galileo board, because we've already read about the Galileo board. It also has this I2C interface, and we can use it for communication on the I2C bus. We know different things that we have on the I2C bus, like we have GPIO chips on I2C bus, 4 GPIO chips on I2C bus actually, and this PCAL9535 GPIO chip, this is the actual chip on the I2C bus. Now it provides an interface to all these GPIO chips, so that whenever we have to use these GPIO chips, all these GPIO chips will use this I2C bus to communicate with the CPU. And we also have this I2C interface, and whenever it has to interface with the CPU, whenever I2C bus has to interface with the CPU, it uses the PCI bus. So whenever we have to talk to the CPU, then we have this PCI bus, and then this I2C bus is on that PCI bus, and we have this 4 different GPIO chips on the I2C bus. So in this way we have these GPIO chips which are dependent on the I2C bus and present on the I2C bus when the I2C bus provides an interface for them, and this is this PCI bus which provides an interface to the CPU for the I2C bus. I2C drivers, let's talk about it. Like I2C drivers, they are basically stored in Zephyr based drivers /I2C. These like all of the I2C drivers that we have are initialized in secondary level. Like we have these different levels. We have primary, secondary, and we have pre-kernel 1, pre-kernel 2, post-kernel, and then application. So out of all these levels, the I2C drivers are initialized in secondary level, and like we have this I2C designware driver, it is initialized in Zephyr based driver /I2C underscore DW.C. This is the place where this designer driver is initialized, like this device underscore init function for this driver is called. It is also a secondary, initialized at secondary level. And whenever we have to use the API, like if suppose there are different APIs given for the I2C drivers, certain functions, so that we could use this I2C bus directly, and to access those API we have to include this hash include I2C.h, which is basically a header file. It contains all the different APIs that are used by that can be used in the application that we're developing. And this PCAL9535 chip, which is present on the I2C bus, its initialization depends upon the I2C drivers. That makes, because PCAL9535 chip is basically on the I2C driver. So to make sure that we have to use this PCL9535 chip, we have to make sure that I2C driver has already been initialized. So if we have to verify this, if we have to make sure that it happens, we generally have this kconfig file in PCAL9535A. In that kconfig file, we can specify that that these drivers, that PCL9535A chip drivers, are dependent upon I2C drivers. So we can mention it like whenever we are defining this PC, we will try to initialize. For that, we have to define some parameters, some configuration parameters, so that it will allow initialization. So for that parameters in kconfig, we can write a single line like depends upon, which makes sure that to specify that PCL9535A chip depends upon the I2C drivers and will not be initialized until the I2C drivers are initialized. So I2C drivers are also dependent in the same way on PCI drivers, as we know that I2C drivers are present. I2C bus is already present on the PCI bus. So whenever we try to initialize the I2C driver, we have to make sure that PCI bus is initialized. This also can be verified or can be checked whether by opening that kconfig file of I2C driver. So in that, it's specified like for certain configurations in which PCI is involved, so we have to make sure that PCI is initialized before that. So for all those K configuration, we could check that it will be written like it depends upon, and then PCI, which is basically the macro, like which will check whether underscore like hash like the value of config underscore PCI is true, yes or no. So it will check whether the PCI has been initialized or not, and then it will try to initialize I2C drivers. So these I2C drivers, there are some APIs that are provided for communication with I2C devices directly. As I mentioned before, like these APIs are present in include/I2C.h, and we can use these APIs directly. So all we have to do is include that I2C.h, and we can have these functions, and these are used for communication with I2C devices. So we have this I2C underscore configure, which will configure operation of a host controller. Then we have I2C underscore write. It will, as name suggests, write a set of amount of data to an I2C device. Then we have I2C underscore read. It will read a certain amount of data from an I2C device. Then I2C transfer. I2C transfer will transfer data from one I2C device to another I2C device. And then we have I2C suspend, which will suspend an I2C driver, and we have I2C resume, which will resume that suspended driver. So these are the API which are provided so that user can, like an application can directly use this API. All you have to do is include that I2C.h. Now I wanted to mention this part because talking about different GPIO pins on I2C bus and I2C bus on PCI bus, we know I2C bus can have different devices, different other devices, and PCI bus can have different other devices other than supporting the I2C bus. So we have to make sure that all the drivers are properly working. So for that, synchronization is very important. As I told you that there are many devices on the same bus. So for synchronization, we have these different APIs: call init, call wait, and call complete. Call init will initialize. Wait is going to provide a space, like it will wait for the operation to complete, and when it's complete, the bus will be open for operation. So we can have these initialization API. So for this, we can have synchronization in between the devices, so that at a time only one device is being used by only one request has been executed among the devices, and all those slaves can actually use it one by one. So That's it. That'll be it. Thank you. So it's done.